Today's lesson is on the atomic mass concept as one of our ways of quantifying atoms. Previous lessons we learned that atoms were composed of protons, neutrons, and electrons. Each of those particles has specific properties unique to each one. We went over those properties. We also found that protons and neutrons have significant mass, and electrons have mass but only about 1/2000th the mass of a proton or neutron. Ordinarily, their mass isn't even considered when looking at the total mass of an atom because their masses are so small. So, atomic mass is the mass of a specific isotope of an element. It's measured in atomic mass units, or AMUs, which an AMU can be written as just AMU, or it could be written also as the mu symbol. This is the mu, or mu. And this is sometimes also used in the metric system. Remember, as micro, if it's by itself, then it's representing the AMU, or atomic mass unit. When we look at the particles themselves, we say that the mass of a proton is 1 AMU, and the mass of a neutron is equivalent at 1 AMU. And this is only to 1 decimal place. So the mass of an atom of an isotope is essentially the mass number of that isotope. So, and that's only because of the 1.0 AMUs. If we add up the number of particles, which is the mass number, then we also have added up the mass with each of those particles having a mass of 1 AMU. Electrons have such a small mass that they have negligible effect, and we generally will not consider them when we're considering atomic mass. So, an atom of carbon-12 that has a mass of 12 AMUs, atom of carbon-13 has a mass of 13 AMUs, carbon-14 has a mass of 14 AMUs. In other words, the mass number of the isotope is the same as the relative atomic mass in AMUs. These are approximations. Masses of protons and neutrons aren't exactly 1 if we go out several decimal places, and also electrons have mass. So we're really looking at to just 1 decimal place. So when we look at the periodic table, we find that we have, for instance, this is lithium. We have the symbol Li, we have the atomic number up here, the number of protons, and then we have this value, 6.941 for lithium, and that is a mass. So the question is, why is the atomic mass on the periodic table not a whole number? We just said that if we add up the number of particles, and we may have something like, with lithium, we may have 3 protons and 3 neutrons. So that's going to be 3 AMUs plus 3 AMUs equals 6 AMUs. But we had 6.941 as a mass, not a whole number like this as if we were counting particles. The answer to that question is that the mass on the periodic table is an average of the mass of all the naturally occurring isotopes. So we may have 3 or 4 different forms of an element or more, and when we look at the mass on the periodic table, we're representing what is naturally occurring on this planet. So the mass on the periodic table is an average of the masses of the naturally occurring isotopes. So lithium has 2 isotopes, lithium-6 and lithium-7. So if we look at that, then we could say 6 plus 7 divided by 2 is going to be 6.5. And remember, we had 6.941 was the actual number. So the question is now, why isn't the average the same as the mass on the periodic table? We just added 6 and 7 divided by 2. This is the value that we get for the average. Why is the average this instead? The answer is that the average is not a simple average. It's actually a weighted average, very much like weighting your grades, where a test counts more than a quiz, which counts more than a homework. So the more abundant an isotope is, the more influence it has on the average. So it's a weighted average, weighted by natural abundance. So every isotope is not equally abundant. If we have two isotopes, we don't have 50% of one and 50% of the other. We may have 90% of one, 10% of another. So the more abundant it is, the more influence it has on the overall average for that element, or the more it's weighted. So if we look at lithium, the abundance of lithium-6 is 7.959% of a natural sample. The abundance of lithium-7 is 92.41 of the natural sample. So obviously this is the one that's most abundant. So the average, which is 6.941, is heavily influenced by the high abundance of lithium-7. Our average is closer to lithium-7 because it's more abundant. An important fact to remember is that the percent natural abundance on Earth is considered to be relatively constant within lifespans on the planet. So lithium-6 and lithium-7 abundance remains constant, and that would be true for any element. So the question would be, how do we determine average atomic mass from isotope masses and relative abundances? Well, first of all, we have to have the isotope masses, and we also have to have the relative abundances. Then we've got to figure out how do we actually calculate that. So calculating an average atomic mass, we end up with this ugly-looking little equation. The sigma is what this symbol is. And that means the sum of. So when you see this symbol, it means the sum of A times M. Now we need to know what A and M represent. A is the fractional abundance. This has to be, in most cases, given. And it is constant on Earth. M is the mass of the isotope, and we'll do this in AMUs. Okay, so as an example problem, let's calculate the average atomic mass of lithium, given that lithium has two isotopes, lithium-6 and lithium-7. Lithium-6 has a mass, as given in AMUs. Lithium-7 has a mass of this. Percentage abundance of lithium-6 is 7.59, while lithium-7 is 92.41. First of all, let's go back a slide to this fractional abundance concept. Fractional abundance. Let's suppose we had 95% abundance. The fractional abundance is equal to the percentage divided by 100. So if we had 95% divided by 100 is 0.95. No percent, it's just a fraction. Okay, so we're always going to take our, since we're dividing by 100, we're going to take our percentage and move our decimal to the right 2 places. Okay, so looking at our sum of A times M. Okay, so that's going to equal the fractional abundance of lithium-6 times the mass lithium-6 plus, that's where the sum of comes in, plus fractional abundance of lithium-7 times mass of lithium-7. Okay. So our fractional abundance of lithium-6 is 7.59%. So that's 0.0759, 2 decimal places to the left, times the mass of lithium-6 is 6.101522 AMUs. That's plus fractional abundance of lithium-7 is 92.41%, so that's 0.9241 times the mass of lithium-7, which is here, 7.016004 AMUs. So the answer to this first multiplication is 0.4566 AMUs plus answer to this second multiplication is 6.483 and 5, and then we add those together and we get 6.940 AMUs. And that would be the final answer. Rounding has us off a little bit in this decimal place, but that's okay. You can see that 6.941 and 6.940 are essentially the same. All right, let's calculate the average atomic mass of argon given the following information. Okay, so we have argon-36, which has this mass and this percentage abundance. 38 has this, 40 has this. So our average atomic mass is going to equal, for argon-36, we got 30.3365, so that's going to be 0.003365 times 35.967546 plus 0.000632 times 37.96272 plus 0.996003 times 39.96283. And you can see this one, 99%. We would expect our average to be very close to this number, because 99, almost 100%, is going to, well, only 0.4% actually is going to be some other mass other than this one. So doing the multiplication, 0.003365 multiplied by this mass gives this number. This multiplication, 0.000632 times this mass, gives this number. And then we have this percentage multiplied by our third mass, which gives this number. We then add the three together, and we end up with 39.947. I'm going to stop it there, 9477. And probably AMUs. And that would be the final answer. So not a difficult calculation, but they can get to be rather lengthy. So far in this lesson, you've learned that atomic masses are primarily due to protons and neutrons, not electrons. Atomic masses are measured in atomic mass units, or AMUs, and atomic mass of a specific isotope is essentially its mass number. Mass on the periodic table that's given to us, that we're going to use almost daily, is a weighted average of the naturally occurring isotopes. And we've also learned how to calculate the average atomic mass of an element in AMUs. We do have a problem with the atomic mass system, however. And that's right here. 1 AMU is equal to 1.66 times 10 to the negative 24th grams. Now, the reason that's a problem is that an AMU is actually too small to be of practical laboratory use. And since chemistry is a laboratory science, that presents us with a problem. The mass on the periodic table appears to be in AMUs, but notice that it has no unit. AMU is not written there. The preferred unit for lab work is one that we can measure easily, and that would be specifically in grams. So it would be convenient if we could assign the gram unit to the periodic table's average atomic mass. In the next lesson, we're going to address specifically this problem in terms of the practicality of the atomic mass system and see if we can come to a solution. Or actually, we'll look at how chemists have derived a solution to this problem. That is the end of this lesson.